We're talking about kinetics. Here's our equation that has the rate constant in it. So here's a rate law, there's the rate constant. Let's just multiply it across. So anything that makes this number bigger will increase rate. Anything that makes this number smaller. So here, if E sub A, our activation energy, goes up, rate's going to slow down. If we ramp up temperature, we're raising E to a smaller negative number and causes rate constant to increase. So here we have some hypothetical reaction, and we think of, at least I think of the activation energy as like a speed bump on a reaction pathway free energy diagram. So let's say our activation energy is 4 kilojoules. Here at room temperature, the molecules that have enough energy to react are given by the area here. If we heat it up a little bit, and here's this root mean square of all your molecules, and you can see now a greater area under this curve. At higher temperatures, more molecules have the required energy. So here's our free energy diagram. Two reactants, they have some kinetic energy. They have enough to make it over this speed bump. They go to products. And of course, as we heat it up, as the previous slide showed us, more of them will have greater energy to make it over this energy barrier. So there's a thing called the double dagger. It's called the transition state, and that's the highest point on the plot. And normally this is where bonds are being broken and formed at the same time. Let's look at that highest point. Highest point in an energy diagram, or points, are transition states. If we have any wells or lower points in between products and reactants, we call that intermediates. So number 3 is kind of important as far as mechanisms go, and that's the rate limiting step. And the reaction step with the highest energy of activation, or the largest speed bump, will be the slowest step and will determine the rate at which the reaction proceeds. It's also sometimes called rate determining step. So thinking about our chlorination of methane again, we have some type of initiation where we have light hitting chlorine and we form the chlorine radical. But here's where the chlorine radical encounters methane and creates an alky radical and some HCl. So at the top of this curve, that's what we got going on. Then we drop down here, and here we have a methyl radical and our HCl. That's the product in the first step. And then we imagine there's some of this in the flask. To begin with, we don't really care how it got there. Point is, it wasn't formed there, and that's why it's there. It's just there. And the methyl radical can now react with the chlorine gas, and there's the transition state for that occurring. And then when that occurs, we get our methyl chloride product, and we formed another chlorine radical. So here we actually see both propagation steps, the formation of the alky radical and the continual formation of a chlorine radical. So here we see all the halides, fluorine, chlorine, bromine, and iodine, and the energy of activation to make this alky radical. And that's the rate determining step, really. So a fluorine radical has a very small energy of activation. And here's a relative rate. I don't know if this is moles per second or minute or probably second. Units really don't matter. The thing is, this is just super fast. We heat it up and it becomes even faster. And here's chlorine. So it has an activation energy of 17 kilojoules, 1300 relative reaction rate. Heat it up, goes up to 18,000. So I think the most important part of this slide is the difference between bromine and chlorine. Well, we can compare all these. So I'll just tell you right here at the beginning. We normally don't do free radical fluorination of compounds because it's too energetic and dangerous, and just melts the chemical plant. Nobody does that. This is just too reactive to be practical. Likewise, over here, this is really slow. Look at these rates. So if you want an alky iodide, you probably don't form it by this free radical reaction. But we can make alky bromides and alky chlorides in industry and academic labs do this all the time. And here shortly we're going to see why bromination is more selective than chlorination. So what have we learned thus far? A large activation energy typically slows things down. So if we increase it, rate decreases. Increasing temperature increases rate. So I just told you fluorine reacts too explosively. So it's not carried out in lab or industry. Chlorine reacts at a moderate speed, and bromine's a little slower, so we can heat it to help it along. And iodine does not react too quickly at all. So we can classify carbons and hydrogens, and you've already seen this with carbons, because I mentioned sec-butyl alky group, T-butyl alky group, and sec-butyl is where we have butane and we form the alky group on a secondary carbon. So if I imagine here's a carbon connected to two other carbons, we call this a secondary carbon. So we can call the hydrogens attached to it secondary hydrogens. So here's a carbon, it's connected to one carbon, so I call this a primary carbon. So likewise, the hydrogens connected to this carbon, we call it primary hydrogens. So here's carbon connected to three other carbons. We call this a tertiary carbon. We're not talking about carbon now, we're talking about hydrogens. So likewise, this hydrogen gets classified as being a tertiary hydrogen. And it's nice that we also talked about these carbons being designated a primary carbon, secondary carbon, tertiary carbon. There was one carbon that got missed, and that would be a methyl carbon. That's a carbon that's not connected to any other carbons. And here it is. Here's our methyl carbon. We're looking at the stability of free radicals. So the least stable radical is called a methyl radical. Call this a methyl carbon. All right, so now we have a primary radical. What's that mean, primary radical? That means we have a carbon with a single electron there, makes it a radical. We call this a primary carbon. We might think also that a primary hydrogen was removed with its, we might say, homolytically. Remember last time we met, we looked what a heterolytic bond cleavage was, and homolytic and the free radical reactions had the homolytic bond cleavage. So, primary radical, primary hydrogens, primary carbon. So here is a secondary radical, because it's on a carbon that's connected to two other carbons. The hydrogen that got pulled away homolytically and left one of its electrons there. The electron it was sharing with carbon, we won't argue about who owned it, get a secondary radical. So here is a tertiary radical. So the more alky groups we can put around a radical, the more stable it is. So this tertiary radical is the most stable. This methyl radical is the least stable. All right, so we're going to pull out propane, some HCl gas, and we heat it up, shine some UV light on it. We see that if we're just making a monochlorinated product, that means we're just putting on one chlorine, we get two products. We get one chloropropane. We can see that there. 1, 2, 3 carbon chain and chlorine there on the end. So here's our one chloropropane. We get that in about 40%. We get a larger percentage of this other product, 2 chlorine. There's 1, 2, 3. There's propane. The chlorine is on the second carbon there. We name this 2 chloropropane. So we might ask ourselves, what's going on here? If I just look at propane, I'll go to this slide. I got 3 hydrogens here and 3 hydrogens there. There's 6, and I got 2 here in the middle. So if it was just statistically the chlorine radical just had to run into the molecule, probability it's going to slam into one of these at a greater probability than those there. So what's going on? We see more of this. And so Wade and other textbooks like to do this to say, well, we have 6 hydrogens here, and if we hook up to these, that's 2 hydrogens, and we get these percentages, ratio that together. You don't have to do any of this math on a quiz or an exam. The point of this is that the secondary hydrogens are 4.5 times reactive as the primary hydrogens. Here's our primary hydrogens. Here's our secondary hydrogens. That's all that's being said here. The most important thing is we see more of the 2-chloral than the 1-chloral. And the question is, why is that? Well, now we're going to go to the propane, the bromine, and we run the reaction. And we see the same phenomena going on where we get less of the 1-bromo, more of the 2-bromo, but it's even more pronounced. We're only getting 3% of the 1-bromo and 97% of the 2-bromo propane. So I might have said earlier when we looked at that energy of activation slide and the relative rates, I told you straight up, bromine is more selective than chlorine. We formed more of the 2-bromo than the 1-bromo. This is more selective. If I go back and look at the chlorine, 60-40. This wasn't as selective. It still preferred the 2-chloral. So bromine is more selective. Bromination is more selective than chlorination. Now the question in your mind should be, well, why do we get more of the 2-chloral? Well, we just saw a slide that says a secondary radical is more stable than a primary. So in the reaction mechanism here, here's our propane, here's our chlorine radical. So this is the rate determining step. This got produced in our initiation step, where some UV light hit a Cl2 molecule and made 2 of these chlorine radicals. And this thing encounters this. Pull out one of these hydrogens, it only takes this amount of energy. Pull off one of these hydrogens, takes this amount of energy. So to form the primary radical, we have a higher energy of activation. We don't care what it was. The slide's saying it's 4 kilojoules higher. So the reason why we form more 2-chloral propane is because in the reaction mechanism, a secondary radical is more stable. And so if we have a flask full of this, more of the molecules make it more quickly over the smaller speed bump than the ones that have to go over the larger speed bump. They go slower to form less of this. And possibly this energy difference is small enough that we get the 40-60. I think there's a little more to it than that. So here's the energy diagram for the bromination of propane. And we still see the same thing that we just learned. We learned that a secondary radical is more stable than a primary radical. And so it makes sense we're going to form more of this. Why is bromination more selective? Well, here we have a bigger energy difference. And this goes slower. We can think about these molecules moving around, and a lot of them come up here and they go, oh, I'm tired, I go back down, I don't have enough energy, I go back down. So a lot of molecules aren't having enough energy to make it over any of the speed bumps. Maybe we heat it just a little bit, and then boom, and we form our secondary radical. And it takes a long time before one goes up over the larger speed bump and forms the primary radical. So we end up with 97 and 3, I think it was. But there's also a little something else going on. This looks exothermic. Look at that. Just this step. These here are lower in energy than these here. If we look at the bromination, this looks endothermic. These are up at a higher energy. So there's this thing called the Hammond Postulate. And it says related species that are similar in energy are also similar in structure. The Structure of the transition state resembles the structure of the closest stable species. So when we have an endothermic reaction, the transition state resembles the product. Exothermic transition state resembles the reactant. So to compare and contrast these things together, the bromination, the transition state looks more like product. In the chlorination, the transition state looks more like the reactants. And so all these things help explain why bromine is more selective. Straight up radical stabilization with the secondary being more stable than primary. It tells us why we always get more of the 2 halogenated product. So here is another visual. So the transition state. It's the highest point in the free energy diagram. It's where bonds are forming, bonds are breaking. The same thing over here. Bonds are breaking, bonds are forming. And if you use your imagination and try and make that Hammond postulate make sense in your mind. Notice they drew this H closer to the Br, and over here they drew the H closer to the carbon, where they say that in an exothermic reaction, Hammond's postulate said the transition state looks like reactants. In an endothermic, they say the transition state looks like products. So carbon radicals are reactive. All free radicals are reactive. What are some other reactive intermediates? Carbocation is reactive. This would be a methyl radical. It's super reactive. And here's 2 other things. Carbanion. This weird thing called the carbene. The most interesting thing for the carbene for me is formal charge. Carbon has a valence number of 4 minus 1, 2, 3, 4. No charge, but very reactive. And here, if we did the formal charge, we'd say carbon has a valence of 4 minus all non-bonding electrons, 1. Half of these here, 3, 1. 4 minus 4 is 0, so a radical has no charge. Reactive intermediates like these are never isolated. They don't live a long time because they're so reactive. Study the carbocation structure a little bit. When you see a picture like this and you see it flat and planar and no electrons in this vacant p orbital, you want to look at that carbon and imagine that it is sp2 hybridized. Flat and planar, 120 degree bond angle, and that's probably the most important thing out of this slide. A carbocation is sp2 hybridized. Some interesting trivia, also called a carbonium ion, and I've never heard this one say. Since we know about primary hydrogens and carbons and secondary carbons and hydrogens, we use this naming to talk about different types of carbocation. Most stable carbocation is a tertiary carbocation. By induction, alkyl groups can donate electron density. You'll learn about that in second semester OChem with our spectroscopy a little bit. So that positive charge is kind of stabilized by these 3 alkyl groups. Here we have a secondary carbocation. It's a whole lot more stable than a primary, and the least stable carbocation is a methyl. So here's our trend in carbocation stability. And notice it follows right along with the radical stability. Tertiary alkyl radical is more stable than a secondary or a primary, and a methyl radical is the most unstable. So our favorite topic, resonance, because we can delocalize charge. That is a stabilizing theme throughout organic chemistry. So here is a carbocation right there. It looks like a secondary. Those electrons can jump over there, putting the double bond there. Now it puts the charge right there. That looks like a primary. These electrons can jump back, goes back. So in nature, this thing exists like this here. Excuse me. So I believe you've had a little bit of practice writing resonance structures where a positive charge moved around. And then you had some practice moving a negative charge around. If a pi bond is adjacent to the Carbocation, the filled p orbitals of the pi bond will overlap with empty pi orbital of the carbocation, and that allows those double bonds to, so here's this empty. So if you imagine a carbon out here in the double bond, and the double bond being formed by that parallel overlap of the p orbitals, you can see they're all kind of what we might say conjugated. Next up, free radical. It looks just like the carbocation, where it's flat and planar, and we want to imagine that carbon being sp2 hybridized. Where's that one electron? It's in the unused p orbital, and we see this order of stability that parallels the carbocation stability. Tertiary radical was most stable, followed by a secondary, followed by a primary, and the methyl radical was the least stable. And we can draw resonance structures of radicals. Now to do this, I draw a half arrow going that way, half arrow going like that, half arrow going like that, half arrow going like that. So these two electrons get together and form a bond there. One of the electrons pulls up there and forms that new radical. And so this idea of charge delocalization on the carbocation, we see a similar effect here. Resonance delocalization is a stabilizing event. It's particularly effective in stabilizing a radical. And this looks about the same. One last reactive species to look at. Carbanions looks very different. I see 1, 2, 3, 4 things around here. It's very similar to what we might think of ammonia looking like, where this pair of electrons is stuffed into a hybrid orbital. So that makes all these sp3. So I got 4 of them. 1, 2, 3, 4. 8 electrons on carbon. 6 bonding plus 1 lone pair. Carbon has a formal charge of -1. Carbanions are nucleophilic and basic. So in summary, carbocations, they're electrophilic. They want electrons because they got that positive charge. Tertiary are the most stable, followed by secondary and primary. A methyl carbocation is the least stable. Radicals, same thing going on. Methyl is the least stable. Tertiary is the most stable. Carbanions, something totally different with the stability, where the methyl is the most stable, the tertiary is the least stable. And that probably goes back to that thing where I said alky groups are electron donating. This thing already has more electrons than it needs. It doesn't need alky groups out here trying to, through induction, give more electron density.